In this video, we will finish the formal proofs of the exponent rules for groups that are written in multiplicative notation. Our author puts the exponent rules inside Theorem 3.23, and you should have already copied this particular theorem down more than once in your notes. We have already proven property 1 and property 2 of this theorem, and in order to do it, we needed the lemma that is now sitting in front of you. This lemma extends the usual way of thinking about exponents when we have a positive integer to exponents that are a negative integer. G to the minus k is the inverse of g raised to the k, or g to the k's multiplicative inverse. In this video, I want to look at proving the third property of Theorem 3.23. Notice it's got two sentences, and the first sentence likely seems like a weird property because you have probably never seen a formula that looks like that inside your high school algebra classes or your lower division math classes at the college level. If we look at the second sentence, it says that if g is abelian, then we do get the familiar formula that if we have gh in parentheses and we want to raise it to the n, we should just do g to the n times h to the n. It's important to realize that in group theory, this is a critically important hypothesis. So let's get started. I want to start with the easy part of this. God damn it! Maybe I could do that. Let's see. I can be lucky and just edit this out. If G is a commutative group or an abelian group, they mean the same thing, then gh raised to the n is equal to g to the n times h to the n for all n inside z. The proof of this is actually pretty straightforward. I am going to break it into two cases. Case 1. N is bigger than or equal to 0. Well, then the meaning of this is gh times gh times gh down to times gh, where we have n copies of the product gh. But we are in a commutative group or an abelian group, so we can break this apart and we can rearrange our terms. And we can write this as g times g times g until we're out of g's, and then we can gather up and look at the h's and multiply h times h times h until we run out of the h's, and we will have n copies of g in that set of parentheses, and we will have n copies of h in this particular set of parentheses. And going from here to here requires the hypothesis that g is a commutative group. Without that hypothesis, I cannot do that. Of course, the next part of this is easy. This set of parentheses is just g to the n, and this set is h to the n by previous work, by the stuff in our previous limits. It's basically the definition of g to the n. Now, to extend this to all integers, I have to think about what if n is negative. That will be case 2. And case 2 is when n is less than 0, and for convenience we are going to let n be equal to negative 1 times k, where k is a positive integer. Now, when we have that hypothesis, we can then do this. G times h to the n will be equal to g times h to the minus k, And by our lemma, we can think about that as gh raised to the k and then take an inverse. And I want to stress that that is by our lemma. But we are in a commutative group. K is positive, so this becomes g to the k times h to the k raised to the negative 1, and that is by case 1. And making a note, g is commutative here. And now what we want to do is we want to think about the inverse. We know what inverses are. That would be hk's inverse times gk's inverse. But let's see, this is going to be h to the minus k times g to the minus k by our lemma. And this will then be h to the n times g to the n, since, remember, n is equal to minus k. And then finally, our group is commutative again, so we can swap the order here and write that as g to the n times h to the n, and that is since g is commutative. And that ends the easy part of statement 3. So before going on, I want to actually write down an important warning, because what we just got done proving requires the hypothesis that G is an abelian group. And if we have G is not a commutative or an abelian group, then we cannot write AB raised to the n is equal to A to the n times B to the n. Because if G is not commutative, there will exist A and B inside the group G with AB raised to the n not actually being equal to A to the n times B to the n. So when we are just dealing with, if all you know is G is a group, do not write AB to the n is equal to A to the n times B to the n. That is a major important warning. So now it's time to look at that weird stuff that the author has as part of his third property of exponent rules. And I want to restate it. What the author tells us is that in a group G, the element gh raised to the n is equal to the element h inverse times g inverse raised to the minus n. And that is a truly weird looking formula. So I want to think about how we would go about proving this. I'm going to actually start by looking at the right-hand side and examining it pretty closely. So let's look at this. If I start off with h inverse times g inverse raised to the minus n, that is, by our exponent rules, h inverse times g inverse raised to the negative 1 times n, and that is nothing more than h inverse times g inverse raised to the negative 1 raised to the n. That is the previous part of Theorem 3.23. So this is part 2 of our theorem. But I also know how to handle that inverse of a product. That inverse of a product is going to be G inverse's inverse times H inverse's inverse, and that mess is going to be raised to the n. But of course, G inverse inverse is just G, and H inverse inverse is just H, and so we actually do wind up having G times H to the n. And so we can say that H inverse G inverse raised to the minus n does indeed equal G times H raised to the n, and that completes the proof of Theorem 3.23.